VinFuture Prize, a new global science and technology prize for humanity from Vietnam. One VinFuture Grand Prize of $3 million. 3 additional special VinFuture prizes valued at $500,000 each. VinFuture Prize honors science and technology work that creates or has a high potential to create meaningful change in the everyday lives of millions of people. Join us to make a change for a better future.
Greetings everyone, and a warm welcome to our esteemed colleagues joining us from all over the world. On behalf of the VinFuture Foundations, I'm delighted to welcome you to the 5th InnovaTalk webinar of 2025. My name is Vi Dương, and it's my pleasure to be your moderator for today. And now, we'll spotlight on one of the most promising materials of our time, graphene. Known for its remarkable strength, electrical and thermal conductivity, and chemical stability, graphene has become a focal point of scientific research worldwide. In this context, the VinFuture Foundation is collaborating with the National Graphene Institute at the University of Manchester to host an InnovaTalk titled Real-World Graphene Technologies from Membranes to Batteries. We extend our sincerest thanks to the National Graphene Institute for partnering with us on these important occasions. Together, we'll explore the exciting progress and also the real-world challenge in advancing graphene from the lab to large-scale impact. And now, it's our pleasure to introduce the chair for today's webinar, Professor Sir Konstantin Kostia-Novoselov from the University of Manchester and National University of Singapore, laureate of 2010 Nobel Prize in Physics and member of the VinFuture Prize Council. The webinar also welcomed 2 distinguished speakers, Professor Rahul Ravindran Nair from the National Graphene Institute, Henry Royce Institute, and the Department of Chemical Engineering, the University of Manchester. Professor Mark Bissett from the Henry Royce Institute and National Graphene Institute, the University of Manchester. Joining them on the panel as a special guest is Dr. Tung Chen from the School of Chemical Engineering, the University of Adelaide. And now, to open today's sessions, we are honored to invite Dr. Tai Ha Lê, Managing Director of the VinFuture Foundations, to deliver the opening remarks.
Thanks, Vi. Good afternoon, good morning, and good evening to all our distinguished guests, speakers, and participants joining us from around the world. On behalf of the VinFuture Foundations, I'm very pleased to welcome you to the 5th InnovaTalk webinar of 2025. Today's topic, Real-World Graphene Technologies from Membranes to Batteries, is one of the most exciting frontiers in science and innovation. Graphene, often referred to as the wonder materials, has captured the imaginations of scientists and engineers across disciplines. With its extraordinary properties, unmatched strength, electrical and thermal conductivity, and chemical stability, graphene holds vast potential to revolutionize diverse sectors, from clean energies to water treatment, from healthcare to electronics. However, as with any groundbreaking innovations, the journey from lab-scale discovery to real-world application is both complex and challenging. That is why today's conversation is so vital. We are especially proud to co-host this webinar in collaboration with the National Graphene Institute, NGI for short, of the University of Manchester. a global hub for graphene research and the birthplace of these remarkable materials. We extend our deep appreciation to Professor Vladimir Falko and his college at NGI for their partnership and visions. Today's event brings together some of the most respected minds in the field, including Professor Sir Konstantin Novoselov, Nobel laureate, and also the distinguished member of VinFuture Prize Council, alongside our esteemed speaker and special guest, like Professors Rahul Nair from NGI and Department of Chemical Engineering from the University of Manchester, Professor Mark Bisset from also NGI at the University of Manchester, and Dr. Tung Chen from School of Chemical Engineering from University of Adelaide. We are grateful to each of them for sharing their time, insight, and experiences with us. So at VinFuture, we believe that scientific innovation must ultimately serve humanity. Through the initiative like InnovaTalk webinar or our annual VinFuture Prize, we aim to foster meaningful dialogue, bridge disciplines and geographies, and accelerate the translation at cutting-edge research into transformative solutions for the world. We hope today's discussion will not only highlight the immense possibilities of graphene, but also, inspire new collaborations, especially for scientists and innovators in emerging regions such as Southeast Asia and Vietnam. Thank you once again for joining us, and I wish you an engaging and thought-provoking session. Thank you. V, over to you.
Thank you, Dr. Taihale, for those insightful opening remarks. And now we are pleased to welcome Professor Vladimir Falko, Director of the National Graphene Institute at the University of Manchester, to deliver his welcome speech.
I'm very happy that this event is taking place. National Graphene Institute has been established, actually have been opened about 10 years ago. We have recently celebrated our anniversary, and during this 10 years, I don't think we ever collaborated with Vietnam, and we would be very happy to extend our links into your country and broaden the collaborations with the South Asia as well. Despite the name graphene in the title of the institute, nowadays we're working on a much broader range of two-dimensional materials, graphene-like, in the sense that they exist in the form of atomically thin materials. And for studying of these substances, we have all the necessary infrastructure to deliver research and to transform this research into innovations. In National Graphene Institute, what we do in research ranges from blue sky fundamental studies of materials to their applications, and applications not just in one industry, but in various industries. You will see examples of what we do today. Mark Bisset and Rahul Nair will tell about their work, but this is just one slice of what we do in National Graphene Institute, not in only graphene, but also in the broader range of two-dimensional materials. Looking to the future, we'll be very happy to collaborate with colleagues in Vietnam. And I also want to mention that for PhD training, we have great opportunities for young researchers to come to work in NGI. We have a doctoral training center, which is called Two-Dimensional Materials of Tomorrow, which is starting its operations this year. Thank you very much for attending this webinar.
Thank you, Professor Falko. And now, to set the tone for today's discussions, let's take a moment to watch a brief trailer that provides an overview of what we'll be discussing today.
Graphene, a one-atom thick sheet of carbon arranged in a hexagonal lattice, has emerged as one of the most promising materials of the 21st century. Celebrated for its remarkable strength, electrical and thermal conductivity, and chemical stability, graphene has captured global scientific attention. Its most compelling real-world applications are found in membranes and batteries, offering crucial solutions to global challenges in water purification and energy storage. In this context, the VinFuture Foundation is collaborating with the National Graphene Institute at the University of Manchester, United Kingdom, to host the InnovaTalk titled Real-World Graphene Technologies from Membranes to Batteries. Chairing the session is Professor Sir Konstantin Kostya Novoselov, FRS, from the University of Manchester and National University of Singapore, laureate of the 2010 Nobel Prize in Physics and member of the VinFuture Prize Council. Having published more than 400 peer-reviewed research papers, Professor Novoselov has been included in the list of the most highly cited researchers in the world every year since 2014. He is an expert in condensed matter physics, mesoscopic physics, and nanotechnology. He was awarded the Nobel Prize in Physics in 2010 for his work in materials science, and most notably for the co-discovery of graphene. Joining him on the panel are two distinguished speakers. The first is Professor Rahul R. Nair, the Carlsberg Royal Academy of Engineering Research Chair and Professor of Materials Physics at the National Graphene Institute, Henry Royce Institute, in Department of Chemical Engineering at the University of Manchester. His current research focuses on molecular transport through subnanometer two-dimensional capillaries and the development of 2D materials-based membranes for energy-efficient separation and filtration applications. Throughout his research career, he has published over 75 highly cited, peer-reviewed articles, including in Science and Nature, as well as several patents on graphene-based membranes. The second is Professor Mark Bissett, currently the head of research and professor of nanomaterials for the Department of Materials at the University of Manchester. His academic research group focuses on the formulation and integration of low-dimensional materials, particularly graphene and other two-dimensional materials, into electrochemical energy storage applications and polymer nanocomposites. In addition to his academic role, he has successfully patented technology which he invented and spun out into a company, Molimem Limited, where he serves as the chief scientific officer. The special guest is Dr. Tung Tran, senior researcher at the Graphene and 2D Materials Research Hub, and a lecturer at School of Chemical Engineering, the University of Adelaide. His research focuses on 2D materials beyond graphene, conducting polymers and nanocomposites for emerging technological applications. Don't miss the opportunity to explore the progress and challenges in transitioning graphene from laboratory discovery to industrial scale innovation. Join us in the upcoming InnovaTalk. Real-world graphene technologies from membranes to batteries.
Welcome back, and without further delay, it's our honor to introduce our esteemed chair for today's sessions, Professor Sir Konstantin Kostya Novoselov. Please join me in giving him a warm virtual welcome.
Good afternoon, everyone. It's really a pleasure to be here and to be back on the panel with my colleagues and friends in Manchester. And when people talk about graphene, of course, probably the first thing which comes into mind is its unique electronic properties and the applications in electronics and photonics. But in fact, the most impactful and the most fast coming and fast developing applications of this material are in fact in the energy sector and in composites and in the area of membranes. All of those three areas are extremely fast developing, and there were breakthroughs in the last few years, not only on related to graphene but in general. And we see how gradually the nanomaterial, and graphene is really one of the leaders here, are changing those applications as well. So it's really, but when we talk about applications, it's of course extremely important, but we are still scientists and we work in the universities. So it's really exciting to see that it's not only about applications, it's in fact about the great science and the which is arising from the applications of graphene into those areas. When you bring the size of your material to one atom thick, you really can expect many new effects, and that's exactly what is happening when we start working with graphene, either in the area of membranes or catalysis or energy applications or composites. So we'll have three very exciting talks today, and I'm really eager to start our seminar. So I guess we'll welcome Rahul first to talk to us about membranes based on two-dimensional materials, including graphene.
Thank you very much, Kostya, for the invitation and introduction. Let me try to share my screen. First of all, good morning, good evening, good afternoon to everyone. I would like to thank VinFuture Foundation for organizing this webinar and inviting me to give this talk. So today I'll be talking about 2D material-based membrane, advances, applications, and challenges. So I hope everybody knows membrane, but as a single word. A membrane means any thin film capable of separating different molecules, atoms, or compound based on different physical and chemical property. So membranes are very important in our daily life since they can contribute to produce clean water, clean air, clean fuel, better medicine, etc. So they are routinely used in several industries for all of these applications. For any membrane, there are certain criteria needed for making the separation process most energy efficient. So membrane should be able to produce high flux. High flux means high flow rate of whatever compound you wanted to separate. And then high selectivity means membrane should be able to distinguish different compounds. And the membrane should be able to stable and it should be able to scalable for practical application. So in our research group at the National Graphene Institute, we are trying to develop new type of membrane based on primarily carbon-based nanomaterials for different separation technology. So when you talk about carbon as a nanomaterial, the first material, of course, coming to our mind is graphene. It's the thinnest material, 1 atom thick. But as a membrane, if you look at the fundamental property of graphene, because of the densely arranged carbon atom in the hexagonal lattice, they are impermeable to even the smallest atom like helium. So it is not a membrane, it's kind of a perfect barrier material which does not let anything to pass us through this graphene. But as scientists, we know how to manipulate material, how to control atoms in materials, so that we did the same. Many people around the world is doing same, controlling the atoms in graphene, making the small pore size, or engineering the pores or holes in graphene to make them as a very efficient membrane for different separation technology. The challenge in this research is we can do this in the laboratory scale, but scaling it up into practically relevant application to large area, meter square or even larger is very challenging. Now, in our research at the National Graphene Institute, we use a slightly different approach. Instead of using single layer graphene, we start using chemically modified or functionalized graphene called graphene oxide. Graphene oxide is an oxidized form of graphene. As you can see, these red and white atoms in graphene are hydrogen and oxygen. And this material is very interesting because it can highly disperse in water. It can solubilize in water. And also we can manufacture this material on a large scale now, on the scale of tons. There are many companies around the world make this material on a commercial scale and large scale. Now we use this material to making membranes, like a thin films deposited on different substrate. And this membrane is not single layer. It's not a single atom thick membrane. Rather, we use the single atom layers to stack them together to make a multi-layer membrane. And the thickness of the membrane can control from tens of nanometer to hundreds of micrometer, depending on what you really wanted to do. If you look at the structure of this membrane, and this is a schematic structure of the membrane, what you see here, it has a layered structure, and each layer is made up of single layer of graphene oxide. And they are stacked on top of each other to make this laminate membrane. And these membranes show some very peculiar properties. For example, they are highly permeable to water, but impermeable to even the smallest atoms like helium. So not only highly selective, these membranes are super permeable to water, means the resistance from the membrane for the flow of water is very, very less. So an example, if you think about if you have a bottle sealed with graphene oxide membrane, and one bottle is filled with water molecule and other one with helium, the one sealed with graphene oxide, the water molecule do not see this membrane at all. They freely permeate through this membrane as if the membrane were not there. So that shows the membrane is highly permeable and there is no resistance for water to transport through the membrane. On the other hand, the bottle which is filled with helium, even as the smallest helium atom cannot permeate or penetrate through this membrane. So that shows the highly selective nature of graphene oxide membrane. So now if you imagine if you put this membrane into liquid or solutions containing different other compounds like salt, for example, seawater. So what you see is that this membrane acts as a molecular sieve. Molecular sieve means it can pass certain molecules to permeate but blocks certain other molecules. It's pretty much similar to our daily life using kitchen sieve, but the difference is the sieve size of this kind of membrane is 1,000,000 times lower than our daily kitchen sieve. So this membrane lets small molecules, like for example, our common salt, sodium chloride, potassium chloride, etc., can pass us through, but bigger molecules like sugar cannot permeate through, or some protein molecules or oil molecules, none of them can permeate, but only small, simple salt-like molecules can permeate. All of these properties are again related to its microstructure. If you look at the microstructure, this membrane is made up of laminar or layered graphene oxide. And each layer has voids between the flakes, and there is a space between the multiple layers. So the molecule has to pass us through these gaps between the flakes to transport from one side to other side. So in normal conditions, like when you're exposed to helium or nitrogen or any other gas, the space is not sufficient for them to pass us through, so it will get blocked. But when you expose this membrane to water, something special happens. The membrane responds itself and get intercalated with water, means membrane expand and create the space so that the water molecules can permeate or penetrate through the membrane. Now, depending on the condition, depending on the concentration of water and so on, this layer distance between the graphene oxide layer can be tuned, and then you can put single layer of water or multiple layers of water through the membrane. So when you expose this membrane to salty molecules, and if the spacing, so we can of course engineer the spacing, and if the spacing is large enough to accommodate this salt molecule, it will pass us through. But we found several methods to control precisely the distance between the layer. Either it could be by physical mechanism or by chemical functionalization. There are many methods available. Many groups around the world is doing this. And by doing so, we control the spacing, and then we can create the membrane which is capable of letting the water, but not the salt molecule as well. So that gives, so this kind of control or tunable pore size of such membrane give us the opportunity for using that membrane for different applications, ranging from energy efficient water desalination or normal water filtration, tunable membrane for food pharmaceutical industry for several process in that sector, and also robust anti-fouling membrane, because these membranes are hydrophilic. They won't easily foul, means the lifetime of the membrane will be high. And also is good, useful for gas separation, hydrogen technologies, and so on. We can make such membrane by several techniques. All are conventional techniques. Basically, we start with a solution and we can cast it into large area membranes. This is a solution cast roll-to-roll membrane production facility at the University of Manchester. We can also create such membrane by a technique called hollow fiber technologies. Means here the polymer is spin into a hollow fiber, and then you coat graphene membrane or graphene oxide inside the membrane as a practically suitable device. On the right side, you can see this is a homemade membrane. So we are in the process of scaling it up. At the moment, we are nearly few meters square. It's a hollow fiber membrane module currently developed for several separation technology. So we are only away from few now. For a commercial membrane, the size is around 40 meters square. So we are few times away from the commercial size. So if you look at the structure of such membranes, basically you take a flat sheet and then coat the graphene oxide or related material on top of the porous substrate, and then you can use as a flat sheet membrane for desalination and water filtration, etc. Or you can coat it on hollow fibers inside or outside, depending on the application, or there are different conditions to tune the membrane. And in all these conditions, what we essentially do is you coat a very thin layer of graphene-based material on top of a porous polymer substrate, and this thin layer act as a active layer which separate different molecules. These are again a couple of examples. We are using such membrane for different applications, from potable water filtration to desalination. And if you look at the data, you can see all the solid data points are from the commercially available different polymeric membrane. And the molecular weight cutoff is essentially the pore size versus the water flux. So all these new membranes have orders of magnitude high water flux, but at the same time, the same material or similar material can be used to tune the pore size from sub-nanometer to tens of nanometer by different techniques. There is also alternate technique to make this membrane. So the previous slide I was talking is graphene as an active layer by coating. You can also make this kind of membrane as a composite. In this case, you add graphene as an additive in a polymer matrix, and then you put it in certain bath, coagulation bath, and convert the solution of polymer with graphene into a solid membrane. It's called phase inversion techniques. And such techniques can make graphene composite membrane or graphene or related material composite membrane for different application. But with graphene and 2D materials, there are also many other opportunities compared to the existing or state-of-the-art membrane available at the moment in the market. For example, if you think about opportunities available for a long future, this is one example. We can control such membrane by an external electrical field that opens the possibility of designing a novel smart membrane for future applications. In this case, what we do is you deposit two metallic porous electrode on top of graphene oxide and apply an electrical field or pass a current through such membrane. And in normal condition, when there is no current, water can flow through the membrane. And when you apply a current across the membranes, as you can see, the needle goes to the high value. That indicates that there is a current passes through the membrane, and in that conditions, water diffusion stops or water permeation stops. The membrane acts as a barrier. And this process is completely reversible, means when the current goes back to zero, water again starts flowing through the membrane. So that shows that it's a responsive membrane. By an external control, like a current or voltage, we can design this membrane as a smart membrane, and this has many applications in separation and also biomimetic membrane for biorelated application. So it's not only responsive, and the membrane, again, the class of material is not just limited to graphene oxide or related. There are many other opportunities. An example is molybdenum disulfide. It's another kind of a 2D material with molybdenum and sulfur atoms on each layer. And we show that such membranes not only smart, but we can also make them intelligent. Intelligent means this membrane has effectively can remember what the conditions these membranes were exposed before. And according to the previous condition, the membrane can behave. For example, in this case, depending on the pH where it was exposed, the membrane can be in the on state, means molecules can permeate, or off state. If the membrane was exposed to acid before, membrane remain in the off state, and when it goes to on state, when it gets to exposed to alkaline condition, it remains there until it goes to certain pH. So this hysteresis in water permeation opens the possibility of defining such membrane for membranes with membrane. And this unique property, again, not going into the details, but related to the structural changes happening in the membrane when you expose to different conditions. For example, when the acid condition, it get hydrogenated. When in the alkaline condition, it get ion exchange with different cation, and these are reversible process. So with that, I would like to conclude, and the main message is there is many potential for this kind of membrane for practical applications ranging from water filtration to separation industries. And beyond conventional membranes and conventional application, there is a possibility of designing smart and intelligent membrane for the horizon. With that, I would like to acknowledge all my collaborators, colleagues, and my mentors, including Professor Andren Gaim and Kostin Avosalev, all my team members, funding agencies, and our industrial partners for their support. Thank you very much.
Great. Rahul, thank you so much. It's really a fantastic talk, and of course, great results over the years. I think we will leave the questions until a later stage, and I would like to invite Mark Bissett to present his talk on using graphene, but also many other 2D materials, including semiconductor 2D materials for energy applications. Mark, please.
Okay, so good morning, good afternoon, and good evening to everyone. Thank you for the invitation to give this presentation today and talk a bit about my research. As they said in the introduction, my name's Mark. I'm a professor of nanomaterials here at the NGI, and my research interests are quite broad, covering a lot of different areas, everything from batteries to composites to membranes. And this slide here kind of gives a very broad overview of all of the different applications or different areas and things that we can do with graphene. And that really is the heart of what I want to talk about today, which is in one word, it's multifunctionality. That we talk about graphene and these other 2D materials as having a lot of different amazing properties. So they have mechanical strength, they have electrical conductivity, thermal conductivity, they're impermeable, they're chemically tunable. And really, it's all of these different multifunctionalities that combined that make them so interesting for a lot of technological applications. So when we're using them in composites, obviously we're using their mechanical properties, but we're also exploiting their electrical or thermal properties or mechanical properties in, say, batteries or membranes or whatever it may be. And so really that's what I think is what makes graphene such an interesting material, is that it's not that it's good at one thing, it's good at so many different things that make it very appealing for a lot of technological applications. So I'm going to kind of talk about a couple of these different areas and some specific cases. So the first one I want to talk about is nanocomposites. So as I said, graphene is well known for being the strongest and toughest material measured. And that makes it ideal for use in a lot of reinforcement for polymer nanocomposites, because you can get benefits for things like lightweighting, because you can reduce the amount of material that you have. You can improve the strength or stiffness. You can get electrical conductivity, which makes it important for conductive polymers. You can have thermal properties, which make it good for thermal management, dissipate heat, etc. But really, again, what the research is really showing is that it's not when you have a single material, a single filler like graphene, that you get the most benefits. It's actually when you get a combination of having multiple fillers, a hybrid composite. So when you combine traditional fillers like glass fiber or carbon fiber and mix that with nanomaterials like carbon nanotubes, graphene, or even carbon black, when we mix these together, how can we actually get something synergistic that gives us the better properties than just one filler? So we want to get the good mechanical, and electrical and thermal and other areas as well. So one example of that is in the case of electrical conductivity. We did a piece of work where we were looking at different dimensionality fillers. So we take 2D materials like graphene and 1D materials like carbon nanotubes and a 0D material, carbon black. And we can combine these together in different ratios and process them into a polymer. In this case, it was in polycarbonate, and we were making composites out of this and then measuring their electrical conductivity and characterizing them. And so when you look at using TEM, if you take a slice of one of these nanocomposites, you can see that the graphene, in this case, tended to form fairly large agglomerates where it isn't very evenly dispersed. The nanotubes actually disperse quite nicely and spread out all through the composite, and same as the carbon black. So when you actually measure the conductivity, that is the electrical conductivity, the polymer is normally insulating. When you add these highly conductive fillers, you can make it conductive. You can see that you can actually wildly vary the amount of filler needed to make your composite electrically conductive. And so whether that's a single filler, you can see that for this graphene, you needed almost 8%, but for the nanotubes or the carbon black, it was more like 1%. And so then we thought, well, what would be interesting is if we can combine these different ratios together to make lots of different hybrid composites. So we mix all of these different fillers together into different ratios, make all of these composites, and then measure all of the electrical conductivity. And we actually see we can get this huge range of conductivities that are available, and we can tune the amount of filler that's needed to actually make these composites conductive. And that's very interesting to industry, because when their industry is making electrically conductive composites for automotive or aerospace applications, they need to know exactly what range it will be conductive. And obviously they want to reduce the amount they have to add into it. But then also you want to get these, as I said, multifunctional benefits where you want it to be mechanically robust as well as electrically conductive. So having the smallest amount of material isn't always the best. Sometimes it's a trade-off between these different properties. As I said, because it is so multifunctionality, as well as being able to tune the electrical conductivity, as Rahul mentioned, one of the good things about graphene is that it can actually be a very good barrier material. It's impermeable to a lot of things. And so you can actually deposit a film or a coating of graphene onto, say, an existing composite. In this case, spray coating a dispersion of graphene onto carbon fiber. And you get these graphene sheets decorated all over the carbon fiber. And actually that works really well as a gas barrier. So that can be used for things like pipes or hydrogen storage vessels or other high pressure vessels. And you can see that even with a very small amount of graphene, 0.05 volume percent, you can significantly reduce the gas permeability. And that's because you're increasing this tortuosity. You're having these layers in the way that are blocking those gas molecules passing through it. So not only have you got electrical benefits, you've now got these gas barrier, or it could also be mechanical properties as well. So one of the work we do here at Manchester is actually braiding and winding of carbon fibers. And so this can be used for pipes or pressure vessels or cylinders or whatever it may be. So we actually see that when we add graphene into these materials, we get a very large increase in the mechanical properties, particularly say the crush strength of it, the axial strength around the outside. And so that, as I said, is very beneficial for things like high pressure hydrogen vessels, where you need to have a good barrier as well as improved mechanical properties. So that's kind of a very short overview of showing some different examples of the multifunctionality that can be used in nanocomposites. In terms of energy storage, as I said, for batteries and supercapacitors and other energy storage, graphene is a very appealing material, and that's partly due to its very high surface area. But one of the problems is when we take graphite as a precursor material and we exfoliate it, and we can get this very nice, well-exfoliated, well-dispersed, high surface area material like graphene, and then we take this and we coat it onto an electrode, or we print it, or whatever we do to it. Normally we end up actually collapsing and losing a lot of that available surface area and get something much lower than sort of theoretically predicted. So what our group and lots of other groups around the world do is look at ways that you can sort of prevent that restacking from happening, whether that be crumpling the graphene into a ball or having other materials in between those layers, preventing them from restacking. And so in the case of batteries, graphene is highly conductive and ideal as a battery additive. This is work we did for a few years ago, was actually incorporating iron nanoparticles in between the graphene layers, again, to prevent them from restacking, and actually forming these iron phthalocyanine molecules. And these keep the graphene layers apart, which maintains a higher capacity and makes it more stable. So without these layers in between, the capacity drops quite quickly. But with the interlayer spacing, you can actually maintain a higher capacity for a higher number of cycles. Silicon or silicon oxide is very interesting commercially for use as a battery anode because its capacity is so much higher than graphite. It can be 4 to 5 times higher depending on the structure. But again, the problem with silicon oxide is it's insulating. And so if we can combine the benefits of graphene, which is highly conductive, and we can have these silicon oxide nanoparticles interspaced in between the layers, we get this large surface area, but highly conductive network. And we see that we can make these kind of structures where we have these silicon nanoparticles in between all the layers of graphene. And when we make batteries out of this, they can be much more stable and last for a larger number of cycles, because these structures can expand and contract and can mechanically absorb those that tension or that force that happens with lithium intercalation and deintercalation that normally leads to the degradation of these batteries. The graphene is mechanically strong enough and also flexible enough that the battery can expand and contract without falling apart and degrading. And so that's one of the big benefits of using a material like graphene, which is mechanically strong, as well as this electrically conductive, and combining it with a material like silicon. For supercapacitors, which work slightly differently from batteries, we see the same thing where when we combine multiple materials together, we get the synergistic improvement. So in the case of if we combine, say, molybdenum disulfide, which Rahul has already mentioned, and graphene together, these are two different 2D materials, one's semiconducting, one's highly electrically conductive. We can mix these together, and the way that they stack can actually give us a higher surface area and work better. Give us higher power density, means that it can cycle faster and provide power over a much shorter time period. But we can also chemically functionalize these by attaching these different functional molecules onto the surface of our graphene or our MOS2. That again prevents this restacking from occurring, or it can, if we alternate the charge of these functional groups, we can control how they restack. So we can alternately get MOS2 graphene layers on top of each other, and these combinations give us much better supercapacitor performance, give us higher energy density, higher power density, which is much better for the commercial applications that we're interested in. And if we look sort of on the nanoscale of these, we can see that the structures we get, we really do get these sort of heterostructures where you've got layers of MOS2 and graphene alternately stacked. They have usually different sizes. The graphene layers are normally much larger. The MOS2 sheets are smaller. And what you end up with is this large conductive backbone, which is the graphene, decorated by these smaller MOS2 layers. And when you stack up these in a much larger structure, as I said, it gives you this much better electrochemical performance. And if we incorporate functionalization as well, these different functional molecules on there, we can get much higher capacities as opposed to when we have the material without those functional groups on them. So that's kind of what I wanted to talk about in terms of giving some brief examples of electrochemical applications and mechanical, and then also building on from what Rahul said. Another area that I work on is on laminar membranes. This is actually work that, as I said in the introduction, was spun out into a company, Molymem, which is based here at the University of Manchester. This technology, very similar to what was discussed in the previous talk on graphene oxide, uses molybdenum disulfide. So we use layers of this MOS2, and these are stacked on top of a substrate in this laminar stack. And then said, because of the interlayer spacing or the charge or whatever chemical modification we do to the surface, we can tune what we allow through these layers. And so the active layer can be as thin as a few microns, and these can be coated onto polymers or other porous substrates. So the work that we did in terms of the commercial journey from the spin-out company, we started out in the lab coating this MOS2 material onto polymers. These are fairly small scale, and then we were working on scaling that up, and we found that actually ceramic substrates, particularly these tubular ceramics, worked much better, and so there was a lot more commercial interest as well. So a lot of our work commercially and academically on these membranes has focused on coating on ceramics. And these can be everything from 20 centimeters long to over a meter, where we're getting each membrane has an area of about 0.3 square meters, so you can stack multiple of these up to get to these sort of quite high surface areas quite quickly. And this is work that we're now developing at pilot scale and commercializing with different partners across the UK and the Middle East, and also in Singapore as well, actually. So just how the technology works, we take these ceramic hollow fiber membranes, and we coat the MOS2 layer on the inside of them, as you can see up here, and we can control the deposition method and also the chemical functionalization that we do, or even the composition of that membrane to tune what we allow through, what we reject, depending on what the use case may be or what particular pollutant we're interested in. And so if we look at the results, these membranes aren't very good for salt rejection. So we're not particularly looking at, when we've scaled these up, we're not looking at desalination, we're looking more at the nanofiltration regime. So this is organic molecules, and this is slightly larger than monovalent salts. Particularly the generation 1 membrane, as we called it, which was a fairly simple structure. The rejection for some of these organic molecules or dyes was quite high and had quite high permeability. Generation 2, which is actually a composite membrane containing multiple materials, we see we get much higher rejections, and the flux rate, and this has been scaled up using real water with contaminants and things like this. We actually take this from utility companies here in the UK. They take their real contaminated water and we run it through our system just to sort of mimic real world performance. We can get high flux and high rejection for these. And because it's on a ceramic, it's a bit more robust and has a longer lifetime than on a polymer. So particularly for, say, developing countries or ones where you want to minimize the expenditure and replacement of these, using these ceramic membranes means that they last much longer, even if they have a higher initial cost, and they don't need to be serviced or cleaned or rejuvenated as often. So in conclusion, hopefully I've shown you very briefly a couple of different examples of how graphene and other related 2D materials can outperform existing materials that are already out there in a wide variety of different applications. In particular, obviously talked about mechanical properties in terms of nanocomposites and polymer nanocomposites, but also for energy storage, such as batteries and supercapacitors. But what I've hopefully shown you is that in each case, the most profound improvements we see in performance is when we can combine multiple materials together. So it's not using graphene just by itself, it's using graphene with nanomaterials such as nanotubes or MOS2 or MaxeNs or other 2D materials or 1D materials. And it's actually a huge amount of variables to play around with when we combine all of these different nanomaterials together to get the best improvement in whatever that application may be. So I'd also like to acknowledge all of my group members and my colleagues here at the NGI, all of the commercial sponsors that I work with, as well as the government funders. And thank you all for your attention.
Great, Mark. Thank you so much. And let's turn now to the last but definitely not least talk of today. And we're going to learn about the applications of graphene in composites. And I'm giving the floor to Dr. Tang Tran, please.
Yeah, thank you very much for Professor Novosnov and future InnovaTalk teams. So this my talk. I will talk in some graphene-based composite material for some practical application. All right, so just everyone knows that Manchester is the name of graphene, but maybe not. Some of you may not know about this. The LA also we're working on graphene research. So in South China, that I'm here, and also I work for the University of LA currently, and it will merge to the other university to make the name of new university, LA University, in the first January of 2026 to make it better in terms of ranking, international ranking. So currently, LA University, one of the top oldest, three oldest university in Australia, and group of 8 best university in Australia. So we have 4 seasons similar to the other countries, but inversely. So now it's the winter there, but winter here, but summer there. So so my research teams are starting to work on graphene here in LA University from 2015. And then after joining a couple of years, we got the funding for 5 years, and from 2017 to 2022 with different university and support from industry partnership as well as the funding agent. So following that, that's another, I think it's similar to Manchester, we got another grant is working on 2D materials. So we expand from graphene into 2D materials, and currently we're working on that with different application as well. So this is the some information about the hub. We have Graphene Research Hub previously, and now we have advanced manufacturing 2D material hub. So it's a combining between the academic institute and industry partnership. It is about 60% of the funding from government and 40% of the partnership, and we work on different things for the from fundamentals to practical application in very different fields. So this is our first teams in 2015. After 2 years joining, we have from small net with a small number, and then we expand very well. Up to now, we have our own facility for research of graphene and characterization, as well as a practical application of graphene and its composite. So in our groups, we have very happy, friendly, and successful driven environment. Interestingly, graphene is bright, everyone knows that, but many ladies are also interested in that research. So we have many members from females to join group as well. We include very young and talented students from bachelor to master and PhD as well. So we proud of some application, and you might know that First Graphene, I think they work with Manchester University as well. So First Graphene start graphene manufacturing by working with us. So we transfer our technology into First Graphenes, and they go very well to make that possible, available on the market now. So the company is located in Perth, Western Australia, the land of graphite miner. And then they also working on different products, including graphene itself with different particle size, controlled very well from 5, 10, 20 micrometer in the size, and the number of layers, majority is less than 10. And they also successful to composite with different polymer. And they make some evidence here is they might make a boot, safety boot, binding graphene and polyurethane. So just for example. So in our group, we try to make graphene more sustainable way. So we use exfoliation method more than oxidation, and we combining the different techniques from the by shear mixing as well as sonication to make them more sustainable processing. And then, yeah, we control very well the number of that. So most of our product is less than 10 years. And yeah, and we also provide working on different kind of morphology. I mean, it can be graphene in seed form majority, but we also working on the particles, I mean, the spherical shape of graphene oxide, but we use a plasma technology to reduce that it to be very fast, like 1 or 2 minutes, and then we don't use much chemicals. So that is currently we're working on. So from that also we similar to the other previous speakers, we also expanded into 2D material. So we work on MOS2, I mean MAXine, TMDs, and phosphorin currently. We also still working on different form of graphene, and we now move on graphene carbon quantum dot, also one of our currently interesting topics. So that is some of product, and that we either transfer into industry partner. So we use a currently 3D printing to make graphene polymer filaments. It can be printed out at a conductive objects. We also working on oil absorbent, heavy metal dyes, membranes, paint, conductive films, sound absorbent, and then a composite. So this is showing some examples. So this is hopefully, if it works with previously maybe not, but it's kind of absorbent, so we can remove the oils by previously we use a pump, vacuum pump to remove oils. But this one you can use graphene combined with a sponge to remove the oils from the water. So you see that it absorbs very well the oils, and then we can remove that. So this is another example that we can actually, it's nothing inside, but we can show that we can actually filter the coke. You can see that. Yeah. So basically, the materials we develop in 3D composite. It can be removed the heavy metals, ions from water, absorb oils or remove the oils or something else. So that is basically the composite of graphene or reduced graphene oxide with polyurethane, for example. So we also develop some examples of coating. So we graphene and polymer composite, and therefore fire retardant application. And you see that this is a control sample without coating, and then with the graphene coating, you can see that it retardant the fire very well. So we also working with the company to develop that products. And not only fire retardant, but also reduce the gas release during the burn. So this is very important thing. So we measure and quantify. It is more than 30% of gas reduced compared with the this commercial fire retardant products. So my group working with the other to make we call smart fertilizer. So we combine graphene with ions, some iron metals to make them possible smart fertilizer. This means it can be released the nutrition very slowly. So just one time fertilize and then it is lasting for long. So that is one of example. We use a controlled fertilizer and then our composite. And actually my boss have licensed this one to US, and they got money every year for this research topic. So it's quite promising. So we also working on using graphene as a construction materials. So we introduce both graphene exfoliation from graphite as well as graphene oxide into the concrete, and then we make the sample to enhance the properties, mechanical property, as well as we target to make that possible conductive, so we can use that structural helmetering in this day. So you can see that with 0.1% of graphene oxide, we can increase about 37.5 in tensile and 77 compression strength, and even more, even better after curing of 28 days. So yeah, this is one of the examples. We also use graphene in construction materials. I'm currently working on that industry-funded project that we use graphene at enhancing the anti-corrosion paint. So basically, we introduce graphene with a small amount, 0.1%, and we can significantly reduce the anti-corrosion rate of that. So that one is funded by industry partner, and then we're working on that. So besides, we also working on the composite to make it transparent conductive. We target to make it transparent flexible films on glass, on PET films, and to make it more conductive, we could even combine with the silver nanowire, for example, so to make it possible replace or comparable with the ITO or FTO. So it is quite success, but of course we have some challenges here as well. So beyond that, we also try to apply graphene. And another thing, I work with one professor in Chile, and then we try to develop the antenna for near field application. And it's quite interesting that we have measured and compared with copper as a reference. It worked very well. Of course, we have something better and something is not what I expected. So graphene also can combine with the MOP, it's metal organic film boards, to make for the sensor application. So I use that material for VOC at volatile organic compounds to detect some toxic chemicals by using graphene combined with MOP. The reason is we try to use MOP at a selectivity components. So we use dentate to print out the different sensors, structures, size, shape, and so on, and we characterize that. So besides that, we also use that as composite, similar to Mark. We use that composite, and it's conductive, and we can use that as a strain or pressure sensor. So that is an example of some of our work, and we also apply it for the cable, construction materials, the bridge, and something that. So finally, I would like to thank the teams leading my managers, Professor Nosey, also with some PhD and research, and as well as industry partner and fundraising. Would like to thank you very much for attention.
Great, fantastic talk and fantastic description of the applications of graphene. I guess now we just jump for quick discussion, and we're running a little bit behind, so let's I'll try to do only a few one or two questions per person here. Rahul, coming back to you. So clearly, a part of graphene, there is another wonder material which you use in your research. It's water, and it's quite a miraculous coincidence that those two work in such an interesting composition together. So what makes graphene to work so nicely with water? And yeah, just if you could explain us a little bit more, how do you control the properties of graphene to turn it all the way from hydrophilic to hydrophobic?
Yes, thanks, Kostya. I think this water graphene affinity is very amazing, and many groups are still trying to understand what is the fundamental origin. I think a clear picture, probably not many people still don't know exact reason, but it has been known from even previous research, like carbon nanotube, water molecules can diffuse or move faster. Is mainly because of the frictional property. The friction between water molecules and graphene or graphitic carbon surfaces is very low. Now, the beauty of particularly graphene is we can make it, for example, graphene can be converted into superhydrophobic by putting functional groups such as fluorine. Fluorographene, a functionalized form of graphene, is superhydrophobic. Water does not likes to wet. But if you functionalize with graphene oxide, it becomes hydrophilic. Water likes to wet. So the tunability makes graphene more attractive to work with molecule water specifically, and we can tune the surface energy, surface wetting property by chemical functionalization method.
And do we learn more about water from the experiments on graphene membranes?
Absolutely. So with this graphene membranes, in general, the fundamental science, what we have managed to get it nanoscale or sub-nanometer scale capillary, 2D capillary. So that leads to a platform to understand what is the structure of water under this ultra-narrow confinement, how the water molecules are moving, how they are diffusing, how they interact with the different surfaces. I think this is ultimate limit what we can study, like it's a one single surface and one layer of water molecules. So both of them are atomically thin. So that gives opportunity to fundamentally probe how these molecules interact at nanoscale. And for example, when we study graphene oxide, we see that these water molecules in 2D confinement, they form an interlocked structure. It's like a 2D ice. And that kind of, each water molecule is hydrogen bonded with nearby water molecules and form a kind of a square kind of lattice kind of structure. And that kind of is very unique, and that kind of correlated structure of water helps it to move faster. On the other hand, if you replace water with another organic molecules, they never form that kind of a structured or crystalline phase of that molecules, and that is why they cannot move faster. Only this kind of fast moving property or fast diffusion is very unique to water.
Mark, while on this topic, can I turn to you? And clearly, because you are working with graphene on large scale and with other material, the self-assembly principles are extremely important in your work. You showed fantastic examples of those self-assembly. How do you control those nanomaterials on that scale?
Yeah, I guess there's lots of different ways that you can do it. The simplest way is through chemical functionalization. If you can make there's some kind of electrostatic interaction between them, if you can have different materials that are, say, positively and negatively charged, you can get them to self-assemble electrostatically. Or if you have a substrate that can be charged, you can have them deposit with an external electric field, for example, interact with an electric field to deposit how you want them to be. It also depends, I think, on when they're being processed, if that's in a polymer or a solvent or whatever it is, what the chemical interaction with that is. So that comes down to the rheology of the interaction between the filler and whatever the solvent or polymer that you're mixing it into, because sometimes you want them to disperse really well and repel each other, and you want them to be really nicely dispersed in the polymer. And other times you want them to kind of agglomerate together. In the case of electrical conductivity, you need to have some agglomeration to form this percolating network. So you don't want them to disperse too perfectly. You want to have a fairly strong interaction between them. So usually, in my case, at least the work I do, it's a chemical functionalization or modification of the surface. And then it's normally an electrostatic or chemical interaction with either themselves or other filler species.
Thank you, Mark. And Dr. Tran, just very briefly, we wanted to come back to you. And so you got a vast experience on the quite a variety of the applications of graphene. Do you see the needs of many different manufacturing ways for graphene? Like I'm still amused or surprised that the largest graphene production these days is still through the graphene oxide. What's your view on this?
Yeah, so yeah, you're right. So currently we have very different ways of making graphene in technologies. So the majority is, I guess, is spin on graphene oxide. So basically we oxidize graphite and after that we correlate it. But there's a lot of chemicals we produce for graphene, for example. So then we try to make something that different. It means we can just exfoliate from graphite. So that's the company wanted. And then we use an electrochemical method. And then yeah, so that can be scaled up and can make that controllable the size. Different in terms of the technique, to be honest, it's very difficult. But they control very well the size of the particles. And then for sure, the different graphene products or production method also will be very different properties in terms of either composite or itself in application. Yeah.
All right. Thank you so much. So I'm turning back to the organizers, please, here.
A heartfelt thanks to our panelists for their wonderful contribution today. And now we'll invite you to watch a short video tutorial on submitting nominations for the 6th season of the esteemed VinFuture Prize. Keep an eye out for the video, and we'll be back shortly with the Q&A session.
Greetings from the VinFuture Prize. Please find instructions for the nominator following these steps. To begin, you can access the nomination portal at online.vinfutureprize.org/nomination. Or you can scan the QR code you see on the screen right now to open the nomination webpage. On this webpage, you can download the instructions and the endorsement letter template. In the instructions, you will find the complete nomination form, where you can draft the nomination whenever you have time. Then, you can copy and paste the draft into the online portal. Please click on Sign Up, and upon successful registration, you can simply use your ID and password to log in. After login, please click Nominate Now to start a new nomination form. Subsequently, you can see 7 content tabs on the nomination form. To begin the nomination process, on the first tab, please select the prize category as well as the type of nominee, whether it is an individual nominee or a group of nominees. Then click the Start button to proceed to the second tab. And we would like to call your attention to tab number 5 and tab number 7. On tab number 5, your evaluation, you're invited to give your evaluation of the nominee's invention, including its groundbreaking discovery, scientific fundamental knowledge, specific approach, uniqueness, and advancement. Then you are required to clarify if the invention can be transferred to a product and highlight its most significant socioeconomic impacts. This includes the number of beneficiaries, such as people, countries, and continents. Additionally, please explain how you believe this invention has or will potentially transform the everyday lives of millions, if not billions of people. Next, please provide information on the history of the invention, such as when and how it started, and who else, except the nominee or nominees, was involved in initiating or contributing to the invention. About tab number 7, supporting documentation and evidence. There are several important documents that the nomination portal and form require. And we would like to call your attention to 3 critical items. The first one is the CV of your nominee or the CVs of your group of nominees if you are nominating a group of people. The second important item is the endorsement letter. 3 endorsement letters or more are strongly encouraged, but 1 is mandatory. The third one is the additional form of nominees. Please be as specific as possible when providing the information. Additionally, you are strongly encouraged to include any valid intellectual properties, publications, patents, or other supporting documents that provide evidence for the nomination. Finally, after filling out and providing all the content in the 7 tabs, please click on the Submit button at the bottom of the page to submit your nomination. If you have any questions or you face any technical issues, please email us at secretariat@vinfutureprize.org. We will be more than happy to assist you in your nomination process. Thank you very much.
Welcome back. And before we move on to the much anticipated Q&A sessions, we'd like to make an important announcement from outside. Submissions for the 2026 VinFuture Prize is now open, including the grand prize and 3 other special prize. We also take this opportunity to remind you of the VinFuture Nominator Recognition Program, which honors those who help identify groundbreaking scientific innovations that with the potential to benefit humanity. And now, the moment you have been all waiting for, the Q&A sessions. It's your chance to delve deeper with our esteemed panelists. Please feel free to actively participate using the raise hand functions. We'll unmute you and give you an opportunity to directly exchange knowledge with our panelists. And for those who prefer a more indirect approach, we encourage you to use the chat box. Simply type down your questions and we will ensure that they reach the most relevant panelists. It's really wonderful to see so much curiosity and enthusiasm from all of you. We have received plenty much of questions coming in. And now to start off the Q&A sessions, I would like to invite one of our audience to directly unmute and talk to our esteemed chair of today's webinar, Professor Novoselov. So, Ms. Ile from Hanoi University of Science Technology, can I have you unmute yourself and turn on your camera and talk to our chair of today's webinar?
Yeah, thank you so much, and thank you all for the talks today. I'm not from the field, but so that's why my question, some may be a little bit naive, and but some other would related to environmental science, environmental issues. Firstly, could you please give me a little bit more information about the development of using graphene for electrical vehicle batteries? And also, what are the advantages of the battery from graphene compared to the available ones? And the second one would be about how to treat it, because I would say that from what I know, it's not easy to treat the battery properly after they are being used. Yeah,
Right.
thank you.
Indeed, one of the largest consumer of graphene, actually the largest consumer of graphene these days is exactly the batteries, and graphene there is used both for cathode and for anode. So it is used mainly in conjunction with silicon to provide when nanosilicon is grafted on top of graphene, and then carbon nanotubes are used as interconnects between individual graphene layers. But also on the cathode side, it is used as a medium to be for the lithium compounds to be grafted on it. So several Chinese companies, the leading producers of batteries for electric vehicles, do utilize graphene in the tens of thousands of tons. You're right that in principle it's we need to recover this, but in that respect, graphene, so in terms of batteries, graphene is not much different from graphite, which is being used in batteries for decades. So in that respect, the presence of graphene in the batteries doesn't present any additional problem. It's actually, it's just you can think about it as part of the graphitic electrodes. So, but though there are of course other issues, and people take the use of nanomaterials very seriously, and say in terms of toxicology, for example, and there are many different research organizations which work seriously on this. Our host today, NGI and Vladimir Falka in particular, they've been running European graphene flagship for many years, and the toxicology and sustainability thrust in this project was one of the largest and taken most seriously. So, but these days we already have medical devices which utilize graphene, and they pass through the clinical trial already. So this serious research into environmental impact and into toxicology paid back, and we can now use this material freely and easily.
Okay, yeah, thank you.
Thank you, Professor Novoselov, and also Ms. Ele, for such a really interesting discussion. And now for the next questions, we have to receive questions to our special guest, Dr. Tung Chen. Dr. Chen, can you please help me to answer these questions? In Vietnam, which unit is currently strong in graphene research, and when you work, what research method do you usually use on materials?
Yeah, thank you for the question. So basically, we have some actually collaboration with some research institutes in Vietnam. I work with VAS, the chemical department in VAS. I mean the Vietnamese Academic Institute of Science and Technology. I work with one group in chemical engineering department, School of Chemical Engineering department in Hanoi University of Science and Technology. I work with one group in Technical University, and one company, that startup company, to produce graphene oxide from bio-waste materials. So it's quite interesting. So there are a number growing in research in graphene in Vietnam, and some of them they go very well. So regarding the graphene material, as all of the members already agree that we have very different kinds of graphene materials, and each of them have their own unique property. So it will be very dependent on application. And then yeah, we can use suitably. Graphene, of course, is show some very potential for some application, especially in environment, construction, composite, in sensors or batteries. Recently, a lot of research on the batteries and supercar. So yeah, so basically, and then yeah, there's a number of groups I work with or consult them with the graphene research, as well as the interesting production by using sustainable technologies from our agriculture products. So that's quite interesting.
Thank you, Dr. Chen, for that wonderful answer. And now, one of our audience has posed a question directed to Professor Bissett. Professor Bissett, does the fact that graphene has very interesting electronic properties, but none of application example actually utilize them mean that graphene electronic applications are not so very successful, or are those success just not around the corner?
Yeah, I think initially a lot of people thought that graphene was going to find its way into sort of traditional microelectronics, find its way in transistors and other electronics applications like this. But one of the problems with that, or one of the things that prevents that from happening, is that graphene is a semi-metal. It has no band gap. And so that means that for traditional transistor electronics, you need it to be a semiconducting material. You need a band gap to have that switching on and off. And so there was lots of research to try and introduce a band gap into graphene, work on doping it, or work on functionalizing it, or mechanical strain and things like this. But actually, since then, there have been so many different semiconducting 2D materials that have been discovered that actually lend themselves much better for the use in transistors and the electronics industry. That graphene has a place in terms of, say, high frequency for terahertz, or for other applications, or even conductive interconnects within circuit design, but not as a silicon replacement, which is what I think initially some people thought it was going to end up being. So I'd say that in terms of electronics, that maybe it's less mature, also because it's quite difficult to work with on those scales. What we're seeing is in terms of commercial applications, as we've already heard today, it's things like battery additives, it's things like composite additives, where it's being used as an additive material, not necessarily being used as in circuitry or electronic components. It certainly has a place in that, but maybe in terms of commercial applications or commercial uptake, that it's seen much quicker uptake in those other areas. So it may be that in the future we see more and more electronics applications integrating graphene. The ones that are using it now tend to be things like thermal management, where you have heat dissipators or things like this, or RFID tags, or it's maybe perhaps different than, say, transistors than what people typically think of when they think of electronics applications.
Thank you, Professor Bissett. And now for our final questions for the Q&A sessions, I would like to talk to Professor Nair. So, Professor Nair, one of our audience is asking that, how does graphene compare to other 2D materials when it comes to ion selectivity and permeability in membranes?
So when it comes to graphene, of course, compared to other materials like molybdenum disulfide or clays, etc., the water if you are talking about water filtration, the practical terms, the water flux is always higher in graphene. But these are of course we can engineer all these things, but in general terms, the flux is higher in graphene related material. And in terms of selectivity or salt permeation property, graphene has much higher opportunity to tune the property by functionalization. For example, you take graphene, you can use graphene as a scaffold to functionalize with any molecules like hydrophilic, hydrophobic, organophilic, organophobic, anything. But if you take other 2D material, that opportunity is very limited because they are less. They can also functionalize, but much restrictions are there. So in terms of changing the materials for our need, changing to get specific selectivity for salt or organic molecule or other molecule, I will say graphene has the more chance, is simply because it's a much tunable material, much versatile material.
Thank you, Professor Nair, and your wonderful answer have ended our engaging Q&A sessions for today. And as we wrapped up today's enlightening InnovaTalk webinar, we extend our heartfelt thanks to our wonderful speakers, Professor Sir Konstantin Kostianopoulos, Professor Rahul Ravindra Nair, Professor Mark Bissett, and Dr. Tung Chen. We are also deeply grateful to the National Graphene Institute at the University of Manchester for their valuable partnership in co-hosting this important dialogue. And to our audience, thank you for your active engagement and thoughtful questions. And please remember that the VinFuture Foundation is opening for nominations for the 2026 award season. We encourage you to nominate groundbreaking research and innovations that can bring meaningful change in science and societies. Thank you once again for joining us today. We look forward to welcoming you in our future InnovaTalk webinar as we continue to explore innovations that serve humanity. Until then, best wishes to everyone.
Yeah. Thank you.
Thank you.
Wow.
Thank you very much.